a derivative? Well, a derivative is just basically a function, just like f of x. Except whenever we write the derivative, we put like a little 1 here. And we call this like f prime x, okay? So this is what a derivative is. It's just a function. So basically what a derivative allows us to do, it gives us the rate of change. So what does that mean? Okay, so we know if we have a linear line, right? We could find what the rate of change is. But let's say this was describing like, you know, the distance of a car and like how the time. So as time is going, the distance of the car is going. But let's be real. What kind of car goes at a really constant rate, constant time and everything? Life is not like that. Life is always going up and down, right? Life is going like this. Maybe not that drastic, but you know what I mean. Maybe he stopped for coffee, maybe there was a car accident, maybe there's a traffic light, maybe he got some caffeine, now he go boom, his speed went up so much. So, you know, finding the rate of change for a line like this is pretty much useless. We need to be able to find the rate of change for something like this. Right? So that's what a derivative is. It basically tells us like the slope of a very curvy line, okay? So, but you're gonna ask me, Wexon, how can you do that? The formula for slope is change in y over change in x, just y2 minus y1 over x2 minus x1. So how can we find the slope? The slope is always changing. Well, we actually find something called like a tangent line. So what that looks like is that every point on this graph, we can pick a point. For example, pick this point, pick this point, this point, you want this point, you want this point, you want this point, any point, right? I can choose any point. And so how I find the derivative is that I'm going to find like the tangent line. So this is what a tangent line looks like. This is what a tangent line looks like. This is what a tangent line looks like. It just touches the graph at one point. So these are all linear, right? So we're basically turning something with curves into something that we can work with using this formula. So, you know, let's see exactly how we can like define this, because this is not really a good definition. So let's see how we can define this. So suppose I have a curved graph like this. Maybe we'll call it like, you know, like this, whatever. So we have a graph like this. Now I'm just going to label some points so that we can get closer to a definition. So let's say this is our x-axis and this is our f of x. We're just graphing a function. So let's call this like x. Let's call this point x. Okay, so what will this point be? This point will just be f of x. And what about like this point? If I told you that this distance is h, okay, h is just a number. So what will this guy be? This guy will be x plus h, right? So this is 2, and this is 2, and this point will be 4. And so what will this point be? This point will just be f of x plus h. Okay, so we're just basically like graphing functions. So we have a point on this, we have a point right here, and we have a point right here. And so I'm going to say, you know, we can make an approximation for this graph by just finding the slope of this. Okay, and what would the slope of this line would be? So we know that this is just going to be a linear line, and slope is just change in y over change in x. So what's the change in y? The change in y is just this, right? This is the change in y-axis. So what is this? This is f of x plus h minus f of x. So let's write it down. We'll write it down here. This is f of x plus h minus what? Minus f of x. Yep. This minus this guy will give us this distance. Okay, and pause. Yeah, so if we have like 10 here, and we have 5 here, so we can find the distance between this just by subtracting the two. So that's why we're going to write f of x plus h minus f of x. So what is the change in y? The change in y is this. is just from this point. I mean, what's the change in x? The change in x is just this. And what is this? This is x plus h minus 8 minus x. So let's say this guy is maybe like 12, and this guy is maybe 6. So again, we just subtract this big guy from the small guy. So we'll put it over x plus h subtracted from x. Okay, great. We have the slope of this line. But you're going to be like, come on, that can't be the derivative. You showed me that the derivative looks something like this. We chose a point, and then the tangent line was like the derivative. But this is nothing like it. Well, we can actually make it look like it, because this is not the complete definition. So what happens instead if I choose not this point, but I chose this point? Then we can find the slope for this, right? Okay, that's good, but that's still not what we want. What if I chose this point? Okay, we're going to draw the line. That's still not what we want. What if I chose this point? Okay, it's getting kind of closer, but it's still not what we want. So what do you notice each time I'm doing? I'm decreasing h, right? So I'm choosing a smaller x coordinate each time. And what is happening to h? Let's say h was 2. H is becoming like 1.5, 1, 0.5. So I'm going to decrease h all the way until it gets super close to x. And as it gets super close to x, it's basically going to become the tangent line. So now we can use our idea of limits to define the derivative. So as h is getting really close to 0, it's getting almost nothing. There's almost no difference between the 2 points. We'll just call it the tangent line. We will say that the limit as h approaches 0 is going to be our derivative. And we can simplify this definition a little more. We notice that there's a positive x and a negative x. So we can just divide this, we can just get rid of them, and we'll just be left with positive h. And there you have it. That's what our derivative is. It's basically telling us what is the distance for the overall function, what is the rate of change for a very curvy function. So this will be our derivative. Now using this definition, let's do a quick example. So let's say we were given a function and we have to find the derivative of it. So for example, we have f of x is equal to 3x squared plus 12. So they're asking, find the derivative of this function. So let's just plug it into our formula. So how do we plug it in? There's kind of a special way we have to do it. So we're going to write out the limit as h approaches 0. And when we write f of x plus h, we're just taking our x. Wherever our x is, we're just going to replace it with x plus h. So let's write it out. 3x plus h squared, right? We just replace the x plus h with wherever we see an x. If we see an x here, we will replace x plus h over here. Okay, and then minus f of x. Well, what is f of f? F of x is just this entire thing, right? So we're just going to minus 3x squared plus 12. Okay, and after we do that, we want to divide by h. Okay, so after we do a lot of algebra, we would expand this, we would simplify, cancel out things in the denominator. It turns out that we will get something like this. Limit as h approaches 0 of 3 and 2 plus x. 2 plus h. 2x plus h. Yep. 2x plus h. So as h approaches 0, what is our limit? Our limit will just be 6x. So that's our derivative. That's how we just found the derivative of this function. So it turns out that 6x is basically the slope of this curvy line. And so that's how we find the derivative using basic algebra and what it is.